Hi, this is Stephen Brower from Martin Valley Community College. This is an addendum to Trees Part 1, specifically showing the downside of the algorithm that we were using. Now, the algorithm the book first introduces in the chapter is a very simplistic algorithm. It may not seem simplistic, but it's a very simplistic algorithm, which does not take into consideration balancing. And so what I want to do is show you the downside of that particular algorithm by going through this example right here. So imagine if the tree initially is empty, and the very first thing that we're adding in is the value 5. Well, I'm just going to, because I know what we're getting to, I'm just going to stick over here. So root is pointing here to 5. So root becomes 5 because this is the first node being added. Suppose the next add we have is 7. Well, remember the algorithm begins, cursor is root, and then it looks, is 7 less than 5? It's not, so it looks to the right. Well, there's no link to the right, so the 7 is added to the right-hand side. And so our binary search tree at the present moment has 7 to the right of 5. So then suppose the next thing we're adding is 5. Well, remember, we're always beginning from root. So 11 is not less than 5. It's greater than. So we look to the right. So we move cursor equal cursor, get right. 11 is greater than 7. Well, we can't go right, so we'll have to create from the right-hand side the new node 11 to the right-hand side of 7. Whoops. A little bit off. That's an 11 there. Okay, so then the next add that's done is 21. So we start at the root. Is 21 less than 5? No, it isn't. It's greater. So we go to the right. Is 21 less than 7? It's not. So we look to the right. We move to the right. Is 21 less than 11? It's not. So we look to the right. There's nothing to the right. So a new link is created to the right-hand side. 21 is now to the right of 11. So now the next add we'll have is 38. So we start here, 38. Well, 38 is greater than 5, so we come to the 7. 38 is greater than 5, we come here. 38 is greater than 11, we come here. 38 is greater than 21, so the 38 is being created to the right-hand side of 21. And just one more giggles and grins, our 62. So again, we begin at the root. 62 is greater than 5, so we go to the right. 62 is greater than 7, so we go to the right. 62 is greater than 11, we go to the right. 62 is greater than 21, we go to the right. 62 is greater than 38. And so the 62 is created to the right of 38. So this would be, in a sense, our worst case scenario that we would have for an add. So with the add method, if the values being added are in increasing order or in decreasing order, then when we're adding in the nth element, we'd have to then go and move n to the right in terms of our, move n times to the right in terms of getting to the next place to add the value. So this is a badly unbalanced tree. So the algorithm that we have is a simplistic one, but this would be the negative, the side effect, a downside of that algorithm. What balancing would have done is by the time 11 was added, it would have reshuffled the tree and made 7 the root. And then by the time it added 38, I don't know about 38. Anyway, I have to do some shuffling again and again. But this one, simplistic algorithm, doesn't do any shuffling, and this is the downside. So yes, it looks like a linked list, but it is a binary search tree. From this node's perspective, everything to the right is greater. From this node's perspective, everything to the right is greater. From this node's perspective, everything to the right is greater. From this node's perspective, everything to the right is greater. From this node's perspective, everything to the right is greater. From this node's perspective, well, there's nothing to the right. But so it is a binary search tree. It's just not a well-balanced binary search tree.